Okay, welcome to video lesson number 10.5, gases in the combined gas law. Now, to understand any scientific law, we need a theory, and the theory to understand the property of gases is the kinetic molecular theory. Point number one of the kinetic molecular theory tells us that gases consist of small particles that have mass. Now, remember, you even measured the mass of air in the under pressure lab and calculated its density. Number two, the volume of a gas is mostly empty space because these particles are super small, and as we've said previously, that they basically have no attraction between them, so they don't stick together, they want to move apart. Point number four, if you look closely, you can see that these particles are in motion constantly, randomly, rapidly, but most importantly, they're straight line motion. So the particles, because there's no attractions, they don't influence the trajectory of each other. They go in a straight line until the next collision where they're redirected in a different direction. Point number five, collisions are elastic, meaning they do not lose energy. So as there's a collision between particles or particles on the side wall of the container, they don't slow down. And remember, temperature really is a measure of the amount of motion. We call that kinetic energy. Okay, the next thing we want to do is look at how the kinetic molecular theory can help explain the relationships between the pressure, temperature, and volume of a gas. And so in these relationships, I'm not so interested in you memorizing the name of the gas law, but just really understanding the relationship. Specifically, whether it's a direct relationship or an indirect relationship. Remember, a direct relationship is one where one variable goes up, the other variable goes up. For example, we said, you know, the more work you turn in class, the harder you try in school, the higher your grade is. So that would be a direct relationship. An indirect relationship is one where one variable goes up and the other variable goes down. So I gave you the example, for example, my spending on Amazon Prime and my bank account. The more I spend, the lower my bank account will be. Okay, so if we looked at, for example, pressure and volume, that is an indirect relationship. So as you, for example, decrease the volume of a gas, the pressure will go up. As the volume of a gas gets bigger, the pressure goes down. So that's an indirect relationship. Next, we'll look at pressure and temperature. That's a direct relationship. So for example, as you increase the temperature of a gas, the pressure will also increase and vice versa. And lastly, volume and temperature, or temperature and volume, that also is a direct relationship. The more you heat up a gas, for example, the more space it will take up. The graph would look similar to the previous one. So now what I want to do is I'm going to look at the PHET simulation that we did in class. This is again compliments of the University of Colorado at Boulder, so we can thank them. And again, I encourage you to go to that website and play around with the simulation to explore these relationships some more. Okay, here we are looking at the PHET simulation. Here's my gas inside my container. Notice the initial temperature and pressure and volume of my gas. So let's look at the relationship between pressure and volume. So as I move the man in, he pushes on the container, and that decreases the volume. Okay. Now notice what happens inside. Because I have a smaller volume, these particles collide more with the side wall of the container. Okay. And because there's more collisions, notice how the pressure goes up. As I decrease again the volume, the pressure is rising. That's an indirect relationship. And the opposite is true. So if I increase the volume of my container, notice now the particles do not collide as much with the side wall of the container, and the pressure correspondingly goes down. Okay? And we can also use the same simulation to note the relationship between pressure and temperature. That one also is a direct relationship. So as I heat up my gas, that causes more motion between my particles as they're gaining kinetic energy. As they're having more motion, notice that the collisions against the side wall of the container are increased. That corresponds to an increase in pressure. Correspondingly, or vice versa, I can decrease the temperature. Notice as I decrease the temperature, the pressure also goes down because there is less motion of my particles. Less motion means less collisions. Less collisions means less pressure. Okay? And then lastly, to show the relationship between temperature and volume, I'll just quickly reset this, put some more gas in, and then will hold the pressure constant, okay? Now, notice as I, for example, decrease the temperature of my gas, and this motion, or this guy takes a little while to kick in here, so I gotta decrease the temperature. Notice my particles are moving around less, and so the gas actually takes up less space. The opposite is also true. As I add heat, that increases the motion of my particles, right? And as the particles move around more, they start bouncing into each other, and my gas expands or takes up more space. So again, that is a direct relationship. Okay, so now what we want to do is solve problems involving changing conditions for a gas. And really we can do that by putting all the variables together in what is referred to as the combined gas law. So simply stated, the combined gas law says that P1 V1 over T1 is equal to P2 V2 over T2, whereas P1 V1 and T1 are the initial pressure, volume, and temperature of the gas, and then P2 V2 and T2 are the final pressure, volume, and temperature of the gas. It's very important that we remember that the temperature must be in Kelvin, because only Kelvin temperature is directly related and proportional to kinetic energy. Okay, so let's solve a couple problems together. So we have a gas at 100 kilopascals with a volume of 2 liters and a temperature of 127 degrees Celsius. Let's say the pressure is increased to 400 kilopascals. What is the new temperature? So I offered you the chart to help organize your variables. I think that's helpful. So let's go ahead and set that up. I make a quick little chart, or I just write down P1 V1 T1 is equal to P2 V2 T2. And then I start to think through and identify the different variables. So it says that my gas is starting at 100 kilopascals. That is my initial pressure, or P1. And it has a volume of 2 liters, so that's easy to identify. 2.0 liter will be V1. And I have a temperature of 127 degrees Celsius. So I might want to write 127 there. Please do not, because you need to recognize this is Celsius. I need to have it in Kelvin. So go ahead and convert that using the absolute temperature conversion. Kelvin is equal to the degree Celsius plus 273. So that would be 127 plus 273 would give me a temperature of 400 Kelvin. Okay? P2, if I go ahead and read on, it says the pressure is increased to 400 kPa, so that's P2. And it says, what is the new temperature? So there's my question mark. I don't know T2. Now, it doesn't say anything per se about volume, so I'm going to have to assume that that is constant right now. Okay? Go ahead and use the combined gas law. So remember, P1 V1 over T1 is equal to P2 V2 over T2. I don't like fractions, so I'm going to cross multiply and make this a little bit easier. So that's going to be P1 V1 T2 is equal to, now I'm going to cross multiply this way, P2 V2 T1. Okay? Now in this form, I could easily isolate any variable I want. In this case, it's T2, so I'll circle that. And then, of course, to get rid of P1 and V1, since it's multiplications, I have to divide P1 and V1. And I can do that legally in terms of math if I do it to both sides of the equation, right? So those cancel. I look at this, and I might even recognize that the volume is constant, so that's going to cancel. I'm going to rewrite that over here as T2, kind of clean it up here, is equal to P2 T1 over P1. Okay? Now in this form, I can now just plug in my numbers based off my chart. So P2 is, if I look, is 400 kilopascals, so 400 kPa. And then I'm going to multiply that times T1. So T1 is over here, that's 400 Kelvin. P1 is right here, that's 100 kPa. So it's very important that you put the right numbers in the right spot, and that's why the chart's so helpful. Okay, so notice that kilopascals will cancel. So really, 100 goes into 400 4 times. So I can do this one in my head without the calculator. T2 looks like it's going to be 1600 Kelvin. Okay, so an example involving pressure and temperature. Now you might recognize that, as we did in class, that this is a direct relationship. And if the temperature is in Kelvin, it's directly related and proportional. So notice in this case that my pressure is going from 100 to 400. So that means it's going up by a factor of 4, meaning multiplied by 4. So I think of what number times 100 gives me 400, that is 4. Okay? And since it's a direct and proportional relationship, I can apply that to my temperature, right? So 400 times 4, notice how that gives me that same answer, 1600. So sometimes you can use that relationship to double check your work and make sure you've done it correctly. Okay? Next problem, we have a gas at 250 Kelvin. It's got a volume of 8 liters and a pressure of 0.5 atmospheres. The pressure is increased to 2 atmospheres. What is the new volume? Okay, so again, I'm going to use the chart to help organize my information. P1, V1, T1. Doesn't take long to write that down. P2, V2, and T2. There they are. So I identify P1. So we've got 0.5 atmospheres. And V1, it says my initial volume is 8 liters. So plug that in there. And then T1, so my initial temperature is 250 Kelvin. Okay? Now, the pressure is increased to 2 atmospheres, so that's P2. It says, what is the new volume? That sounds like this one right here, V2. Okay? And again, it doesn't say anything about temperature, so I'm going to assume that that's being held constant in this case. Go ahead and apply the combined gas law. So P1 V1 over T1 is equal to P2 V2 over T2. I cross multiply again, and I'll do it quicker this time since we've already went through it once. P1 V1 T2 is equal to P2 V2 T1. Okay, so in this form, no fractions, don't have to fear fractions. I look and I need V2. Which one is that? That's this one right here. So to get V2 all by itself, I'm going to divide both sides by P2 T1, divide by P2 T1, and again I can cross that out. Now I got V2 by itself. I can even, as I look and see that the temperature is being held constant, I can get rid of T1 and T2 because any number divided by itself is 1. Let's clean this mess up. We got V2 is equal to P1 V1 divided by P2. Okay, so let's go ahead and plug those numbers in. And again, I got my chart here, so that's nice and easy. We got 0.5 atmospheres, and we've got V1 is 8 liters divided by P2, which is 2 atmospheres. Okay, so I just plugged in my numbers. V2 then is going to be equal to, notice my atmospheres cancel, 0.5 times 8, or yeah, it would be 4. 4 divided by 2 would be 2. So my final volume would be 2 liters. So again, I can do that. It's 4, half of 4 is 2, so V2 is 2 liters. Okay. Again, you can use the relationships, noticing that pressure and volume are an indirect or inverse relationship. Okay, so it looks like my pressure is increasing by a factor of 4. So 0.5 times 4 gives me 2 atmospheres. So that means my volume is going to go down by a factor of 4. So 8 divided by 4, notice, is 2 liters. So the relationships, again, can be helpful to predict and also check your work. So again, I hope that was helpful. I'll see you in class.